Now, before we can talk about the oxidation of alcohols, it's important that we can classify alcohols because they will react differently in oxidation reactions. So we'll start with our first here. This is a primary alcohol, which we can spot because the carbon that is attached to the OH group only has one other carbon attached to it, right? Another way that we can represent that, if you like more kind of displayed-ish, not fully displayed, but not skeletal, then if we've got our COH, then attached to the C with the OH, we've got two hydrogens, and then we've got our R group, which is where we've got, our other carbon. So in general, RCH2, OH. Now for our next one, this is a secondary alcohol, and hopefully you can start to spot what's going on here, where we've got attached to the carbon that's got the OH on it, we have now got two carbons attached to that carbon. Or if we want to look at it again more displayed-esque, then we've got our C, we've got our OH, and then attached to that, we've only got one H, and then we've got two R groups, where those R groups are your alkyls with carbons, etc. Or in other words, we can write that as R2CH OH. And then our last one, you can probably do this for me, maybe you've even skipped ahead. On the carbon that's got the OH attached, we have got three carbons attached to that carbon. This is our, of course, tertiary alcohol, showing that again in a similar way. We've got our COH, and attached to that carbon, we've got no H's, we've just got R groups. We've just got, more carbony things. Or in other words, R3COH. So now, again, before we get into the oxidation, we've classified our alcohols. Let's make sure that we know what oxidation and reduction mean, so we know what we mean when we say that we are oxidizing an alcohol. Now, in your physical chemistry and in some of your, spoiler, and in some of your inorganic chemistry as well, you will have seen oxidation as the loss of electrons. You may have seen it as the increase in oxidation state or oxidation number. But in organic chemistry, which is where we are going to see it more commonly as the addition of oxygen or the loss of hydrogen, more likely the oxygen one, because oxidation, oxygen, duh. For reduction, it's the opposite. Reduction is the gain of electrons. It is the decrease or reduction, duh, in oxidation state. But in organic chemistry, which is what we care about right now, we can think of it as the removal of oxygen or the gain or the addition of hydrogen. Now we've got our alcohol classification, we've got our redox definitions. Let's smush them together so we can look at the equations for the oxidation of alcohols. Now, when it comes to oxidizing alcohols, we need an oxidizing agent, and the most common oxidizing agent that you will see used is acidified potassium dichromate, which if we write that out as the formulae, we can see that that's our potassium dichromate, K2Cr2O7, and then acidified means that we've added acid, and the acid that we would typically use is sulfuric acid. Now, lucky for us, when we're writing balanced equations showing the oxidation of organic species, particularly alcohols here, we will not write the potassium dichromate in our equation. Instead, we can just represent our oxidizing agent using an O in square brackets, and that makes everybody's life so much easier and helps us to balance really nice and simply as well. So let's start with the oxidation of primary alcohol. This is going to be the most involved one, and the others are going to seem so simple in comparison. So for primary alcohols, if we add our oxidizing agent, just one lot of it, then we are going to oxidize that to an aldehyde. Now, an aldehyde has got the functional group CHO. We've got a carbonyl, but that's at the end of the chain. So C double bond O and then an H to show, well, it's at the end of the chain. So this is these are H's, not M's. I've just got maybe terrible handwriting. So this is an aldehyde. Now this so far equation, or this equation so far, rather, sentence, is not balanced, right? If we just count the H's and O's, on the left-hand side, we can see probably the easiest one to spot is that we've got two O's. The O in the oxidizing agent brackets counts, we can treat it like an oxygen. We've got two O's on the left, but we've only got one O on the right, which means we must have another product that has an oxygen in it. Now you might be able to guess what that product is, because if we also count the hydrogens, we can see that on the left we have got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, whereas on the right we've only got 6 hydrogens in our aldehyde. So we've got 2 hydrogens left over, and so that must give us H2O, right? 2 H's. Where's my highlighter? There we go. 2 H's from the alcohol. And then do we necessarily know which of these O's it is, whether it's this one or this one? Let's say H2O, like that. Okay. But this aldehyde, this product, can actually be oxidized further. So this first stage is only partial or incomplete oxidation, because we can now take the aldehydes that we've just formed and we can react that with the oxidizing agent further, and this aldehyde will be oxidized to a carboxylic acid. So we'll end up with, for our functional group, C double bond O OH, which is our carboxylic acid functional group. I'm going to write it to the side just so that I don't run out of space. Now I can comfortably write this name to the side because there's actually no byproduct for this second stage of oxidation. Because if we just count our C's and O's and H's, C's of course, there are just 3 on both. For our O's, we've got 2 oxygens on the left and we've got 2 oxygens on the right, so that's already balanced. And then for our hydrogens, we've got 6 hydrogens on the left, we've got 6 hydrogens on the right. So there is not an additional water molecule that's released in the second stage of our oxidation. So we've got our partial oxidation, and then we've got our further oxidation of our aldehyde to our carboxylic acid. Now, if we wanted to write this all together, right, because we can go alcohol to aldehyde, aldehyde to carboxylic acid, or we can write this as one overall equation. Let's even just make the space, where if we were to smush these two equations together, we can have our alcohol, we can add 2 lots of our oxidizing agent. That will give us our final complete oxidation product, which is our carboxylic acid. And as our byproduct, we will just have 1 water molecule, again, because we release a water molecule in the first step, but we do not release a water molecule in the second step. So this here at the bottom, this is just our complete oxidation if we were to put both of those oxidation steps into one overall equation. Now, you might be asking yourself, or you might just want a reminder because you've seen this prior, what if we want the aldehyde? How do we stop the aldehyde from being oxidized all the way to the carboxylic acid? What if we actually wanted the aldehyde as our product? Well, the reaction conditions can actually dictate or determine which oxidation product we will collect. So if we only want partial oxidation, so we want to collect the aldehyde, then we are going to have to use distillation. And the reason that we're going to use distillation is due to a throwback to intermolecular forces and boiling points. So if we just do a quick label of our setup, I won't do a full label and a full explanation. That will be in the RP5 practical video. But just as a general kind of making sure that we know what's going on, within our round bottom flask, we've got our reaction mixture. And in our reaction mixture, we have got our alcohol, reactant alcohol. We've got our oxidizing agent, so our acidified potassium dichromate, right? We're then going to heat this up. Okay. So as the reaction is taking place, heat, 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 reaction, 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 the aldehyde, as soon as the aldehyde is formed, the aldehyde actually has a lower boiling point than whatever the alcohol was. And the reason the aldehyde has a lower boiling point is because alcohols have hydrogen bonds between molecules, which are stronger than the dipole-dipole and van der Waals forces between aldehyde molecules. So because the aldehyde has the lower boiling point, as soon as it's formed, it's going to, well, not necessarily as soon as it's formed, but at a lower temperature than the alcohol, it is going to vaporize and start to rise. And then it's going to start to travel down our Liebig condenser. Again, full labeling in the RP5 video. And as the aldehyde vapors travel down the Liebig condenser, they're going to cool, condense, and then that's what we're going to collect in our receiving flask. So the aldehyde collects here. Right? Again, these are my lovely squiggles, are the aldehyde vapors. Once more, the reason it's just the aldehyde vapor and not the alcohol vapor is because we have not yet reached the boiling point for the alcohol. The aldehyde has a lower boiling point than the alcohol, so at a lower temperature, the aldehyde, once it's formed, is going to vaporize and able to be removed and collected. That means because it's removed once it's formed, it's not going to be able to react further to give us a carboxylic acid. So distillation allows us to collect the aldehyde because we get partial oxidation. Now, if we wanted this reaction to go to completion and collect the carboxylic acid, then we would have to heat under reflux. Now, how does this work for reflux? Again, we've got our reaction mixture down here. I'm just going to call it reaction mixture this time because we know what's in here. And we are, once again, we're going to need to heat this up. More details on the heating in our RP5 video. Okay, so we're going to heat the reaction mixture up. Reaction's happening. Lovely, lovely, lovely. Once more, the aldehyde is going to be produced and it's going to vaporize at a lower temperature than the alcohol. And so once more, our aldehyde vapors are going to rise up the condenser. Okay, the difference here now is because of the setup, because it's vertical, once those aldehyde vapors have risen up the condenser is going to start to cool and condense those aldehyde vapors. And what does that mean? It means that the vapors are just going to fall back down into the reaction mixture. And if they fall back down, then they're able to react further to produce the carboxylic acid. To really, really make sure that the reaction goes to completion, we might also want to use excess of our oxidizing agent. We want a lot of it because we need the reaction to essentially happen like 2 times over. So we need to make sure there's enough of our oxidizing agent to allow the reaction to go to completion. So here we've got our aldehyde vapors rise and they fall. They fall back down once they are cooled and condensed. So if we want our aldehyde distillation for partial oxidation, if we want our carboxylic acid reflux for complete oxidation. Now we've covered the hard part, secondary alcohols. are so much simpler because there's only one possible product. If we have a secondary alcohol, again here where we've got two carbons bonded to the carbon with the OH, then we're going to add our oxidizing agent, same oxidizing agent, acidified potassium dichromate, same representation of our O in square brackets, and our product, there is only one possible product and we love to see it, and that is a ketone. But we have a carbonyl group, but it's being formed somewhere within the main chain. So remember aldehydes from before, those were formed at the end of carbon chains, whereas ketones, same C double bond O, but this time formed within a chain. So this is a ketone. To make sure this is balanced, let's just count our oxygens and our hydrogens. We've got two oxygens on the left. We've only got one here on the right, which means we must have, well, we can probably guess what it is. We've got eight hydrogens on the, we don't have eight hydrogens. One, two, three, four, five, six, seven. We've got 10 hydrogens on the left. We've only got eight hydrogens on the right, which means, of course, we are going to produce a water molecule. And that is it, right? For secondary alcohols, we're always just going to produce a ketone plus one water. Nice and simple. Finally, and I can even put it on the same slide, tertiary alcohols. So I'm going to draw an example. Let's even take similar to this. Let's say that we had our OH here, but instead of an H down here, we had another CH3. Okay. Now, if we try to oxidize tertiary alcohols, I mean, good luck, right? With acidified potassium dichromate, this is not going to oxidize a tertiary alcohol. So we're not going to get any reaction and we don't need to write an equation because we're just going to keep the alcohol as it was. Should we do a practice question? I mean, while we're here, we might as well. Let's do like a relatively tricky one. We want to write a balanced equation for the complete oxidation of the organic compound below. So we're not going to rush. We're going to look at each alcohol group in turn and figure out what's going on. Because here we've actually got three alcohol groups and they are different classifications of alcohol. So let's just start left to right because I don't know, why not? If we start over here, this OH is a tertiary alcohol because this carbon that it's attached to has got one, two, three carbons attached to it. So because this is a tertiary alcohol, which I'll represent with a three and a little circle, this is not going to undergo oxidation at all. It's going to stay exactly as it is. Now let's go to our next OH. This is attached to a carbon that's attached to just two carbons. So this is a secondary alcohol. So this is going to give us a ketone. And it's also going to give us one water molecule. Now for our alcohol group at the end, this is a primary alcohol because the carbon that is attached to the OH only has one carbon attached, so primary, which means this, and reading the question carefully, where this is going to be complete oxidation, this is going to give us a carboxylic acid. Okay, now because primary alcohols are oxidized in two stages to carboxylic acids, we're going to need two lots of our oxidizing agent, but we're only going to produce one water molecule. As we saw before, we only produce the water molecule in the first step. We don't produce the second one in the second step. So let's now write out the equation. I've just copied and pasted my reactant again here because I don't want to write it out again. Okay, and let's write our equation. So we're going to start by reacting this with our oxidizing agent, which is our O in square brackets. Now, how many of these do we need? Well, we needed one to oxidize the secondary alcohol to the ketone and two for our primary alcohol to the carboxylic acid. So we're going to need three of those in total. Now, what is our organic product going to look like? Oh my goodness. Okay. So we're going to have, it's a 5-carbon chain. Starting just left to right, we've got CH3 up here. Our first OH, our red OH, is going to stay exactly as it was because it was tertiary, nothing happened. On our next carbon, though, the secondary alcohol is going to be oxidized to a ketone. So we're going to need to change that to a C double bond O. Careful not to add too many hydrogens. This carbon now has got all of the bonds that it needs. Let's keep moving across the molecule, CH2. And then for our last carbon, instead of a primary alcohol, we've now got a carboxylic acid. So like this. This isn't done yet because remember, for our oxidation reactions, we're also going to produce water. The question is how many water molecules? Well, luckily we planned this all out. We're going to get one water molecule from the oxidation to the ketone, and then one more for the oxidation to the carboxylic acid, so plus 2 H2Os. Okay, questions like this, where you've got multiple alcohol, multiple hydroxy groups, don't rush it out, figure out what's happening to each group, and then how many oxidizing agents, how many waters as a result. For more A-level chemistry support and practice and explanations, make sure that you have subscribed, make sure that you like this video, and leave a comment if you've got any questions or you just want to say, yay, I get it now. And I'll see you in the next one.